Hello, welcome back to Educator.com and welcome back to AP Calculus. So today we're going to do some example problems for the concepts that we've been discussing the last couple of lessons, which is slopes of curves. Let's jump right on in. Okay, this seems like a long problem. It's not. It's just there's a lot of information in it. That's all. We just have to sort of keep track of this stuff. Okay, so a large tank can hold 600 gallons of water. It takes 25 minutes to fill up the tank. At various values of time, the volume of the tank is measured, and the table below gives the appropriate data. So I think I'm going to work in purple. So here we have the time in minutes, volume in gallons. So at the beginning, there's nothing in the tank. 5 minutes later, there's 30 gallons. 10 minutes later, 100. At 15 minutes, there's 220. At 20 is 350. At 25, that's 600. So this is a tabular representation of a particular function. A, which is the independent variable and which is the dependent? What is the average slope between T0 and T5, between T5 and 10, between 10 and 15, 15 and 20, and 20 and 25? So we want the average slope. That means 2 points. Here are 2 points, 0, 0, 5, 30. So it's going to be 30 minus 0 over 5 minus that. For the average slope between 5 and 10, it's going to be 100 minus 30, 10 minus 5. Express these slopes as rates of change and interpret what these mean physically. And D, what is the instantaneous slope at t equals 20? In other words, exactly when the clock hits 20 minutes, what's the instantaneous slope? Not average. So we can find an average between 10 and 15, or 15 and 20. We can find an average between 20 and 25. We want the instantaneous at 20. And what does this mean physically? Okay, let's go ahead and get started. So part A, which is the independent variable and which is the dependent variable? Let's look back at the question. The volume in the tank is measured. Anytime something is measured, that's the dependent variable. It's that simple. So volume is the dependent variable, time is the independent variable. Therefore, what you actually have is volume, which is the dependent, is a function of time. I just small t here, I ended up with a capital T here, it doesn't really matter. So volume is a function of time. So in this particular case, this function is expressed as a table. You're going to see functions expressed in 3 ways primarily: as a table, as an actual graph, or as an actual function that they give you. Like, let's say v equals 13t cubed, an explicit equation. So a function can be given to you as a table, it can be given to you as a graph, it can be given to you as an explicit function. In this case, the table tells us, because we know that volume is measured, it tells us that volume is a function of t. We don't have the explicit function, but that's okay. You know, we have the table of values, so we should be able to extract some data here. So that takes care of A. Okay. Now, what is the average slope between t equals 0, t equals 5, and all that business? Okay, so let's go ahead and take care of that next. But I'm going to actually draw this out so you can see it, so we can convert this into some sort of a graph. So let me at least go ahead and do that. So I'm going to take 5, 10, 15, 20, 25. 5, 10, 15, 20, 25, and I have 1, 2, 3, 4, 5, 600. So this is 100, this is 300, and this is 500. So I'm going to graph my points. I'm going to plot my points. Well, my points were at 0, it was 0. At 5 minutes later, it was 30. So I'm going to go ahead and put my point there. At 10 minutes, it was 100, so it's right there. At 15, they said I had 220 gallons, so maybe someplace like that. At 20 minutes, they said I had 350 gallons, so 1, 2, 3, maybe someplace like that. And at 25, I had 600, so someplace like that. So this is the graphical representation. Now, we said that and this was volume, right? And this was time, t. So volume was some function of time. Now, this gives us discrete values, individual ones. It's pretty fair to say that. Let's go ahead and do this in black. So if I were to extrapolate, I'm looking at some sort of a function like that. There you go. So if I need to deal with anything in between. So the idea is there is another branch of mathematics called numerical analysis where you can actually find the best fitting curve that matches these data points, because I only measured it for these, 5 or 6 values. But the idea is that it is some function that we actually can make continuous. It's a nice smooth curve. Okay. So we said part B. So we wanted to find the average slope between here and here, here and here, here and here, here and here, here and here. Well, essentially what we're doing, average slope means, let's go back to purple, means find the slope of that line segment, 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 find the slope of that line segment. That's what we're asking. Average slope, secant line, the slope of the secant line, the line that connects 2 points on the graph. Okay. So let's go ahead and do, yeah, I guess I can do it here. It's not a problem. So let's go ahead and do, so average slope between 0 and 5 minutes, that's going to be volume final minus volume initial over time final minus time initial. Well, the volume here was 30. The volume here is 0. The volume here, I'm sorry, the time here is 5. The time here is 0. So we have 6. Okay. Now, the average slope for the time interval 5 to 10. Now we're finding the slope of that. So this is going to be a certain xy value. This is going to be a certain xy value. So again, it's going to be delta y over delta x. And the delta y's, it's going to be, when I look at the table of values, at 10, the value was 100. So it's going to be 100 minus the value here, which was 30, over 10 minus 5. And this value is going to be 14. The average slope from 10 to 15, I take a look at the y values and I divide by the difference in the time values. It's going to end up being 220 minus 100. 220 is the y value at 15. 100 is the y value at 10. Over 15 minus 10. And I get a value of 24. The average slope on the time interval from 15, to 20, it's going to end up being, so at 20, the value is 350. And at 15, it is 220. Of course, this is 20 minus 15, and I get 26. And then the average value from the final time interval from 20 minutes to 25 minutes, well, the y value at 25 minutes is 600. That's this line segment right here. The y value at 20 is 350 divided by 25 minus 20, and I get 50. There we go. So I've got 6, 14, 24, 26, 50. These are the average slopes from these time intervals. 0 to 5, 5, 10, 10, 15, 15, 20, 20, 25. That's it. That's all I'm doing. You know what average slope means? Find the slope of the secant line. 2 points. Okay. Now let's take a look at part C. Part C asked, it said express these slopes, these average, express these average slopes as rates of change and interpret them physically. And interpret physically. Okay. Well, we said in the last lesson, so let's just take 0 to 5. So our 0 to 5 time interval, so we said that the average slope was 6. Well, we know our function was volume is a function of time. Therefore, volume is expressed in gallons, that was the unit, per 1 minute, right? The independent variable, the unit of the independent variable is in the denominator, the unit of the dependent variable is in the numerator, so the 6 is the numerical value of the slope, physically 6 gallons per 1 minute. So what this says is, on average, because we calculated an average slope, on average, over the time interval 0 minutes to 5 minutes, the tank is being filled being filled 6 gallons for every 1 minute that passes. For every 1 minute that passes. That's what this is saying. Okay? 6 is the numerical value that I found for the average slope. Well, the volume, gallons, is a function of time, seconds, or in this case actually it was minutes that we measured it in. So it's 6 gallons per minute, or 6 gallons per 1 minute. So in general, on average, between 0 and 5, for every minute that passes, 6 gallons of water is being added. That's the physical interpretation. This is a rate of change. It's the rate at which the volume changes per change in time. It is a rate of change. How fast something is changing per something else. So when you hear rate, there's a per in there somewhere. Has to be. Okay. Next one. Let's not do all of them. Let's just do so 0 to 5. I'll skip the 5 to 10. I'll skip the 10 to 15. Let's do the 15 to 20. It's the same thing. So the time interval from 15 to 20, the numerical value that we found for the slope, the average slope, was 26. What that means is that it's actually 26 over 1. It means 26 gallons per 1 minute. So, on average, during the time period between 15 and 20, for every minute that passes, 26 gallons is being pumped into that tank. It's a rate of change. The change in the volume per unit change in time. That's all that's going on. And we might as well go ahead and do the last one. 20 to 25, same thing. The numerical value that we ended up getting, I think was 50, if I'm not mistaken. So this is 50, which is the same as 50 over 1. That means 50 gallons per 1. Was it 50 that I got? 250, yeah, okay. Oh, all right. Gallons over 1 minute. So during the time increment from 20 minutes to 25 minutes after I started filling up the tank, during that time, on average, for every minute that passes, I'm adding 50 gallons to the tank. The volume is changing 50 gallons per 1 minute. It's a rate of change. Now notice that these rates of change are not constant. Between 0 and 5, it's 6 gallons per minute. From 15 to 20, it's 26 gallons per minute. 20 to 25, it's 50 gallons per minute. So the rate of change is changing. The average slope is changing. It's filling up faster for every minute that goes by. More water is being pumped in. It's like I'm turning the faucet, and for every moment that I'm actually opening up more and allowing more water to flow in. So, okay, so let's see what we've got. Instantaneous. See if I've got one more blank page. I do. So part D it asks for the instantaneous slope. Instantaneous slope at t equals 20. Okay. And they also want us to interpret this physically. Interpret physically. Okay, so now, so far what we've done is we've calculated averages. Now we want an instantaneous. What they're asking us to find is a derivative. They're saying 20 minutes after I start filling the tank, exactly at 20 minutes, how much water is being pumped into that tank in gallons per minute. They want the instantaneous rate of change. They want the derivative. Well, how do we find the derivative? Well, in the previous lesson, we said the only way to find the derivative is to find some function. Whatever this function is, v equals f of t, some explicit function. To find the derivative, to differentiate it, to find that derivative and then plug in 20 into that. But we don't have that here. However, there is a way to do it graphically, and that's what I'm going to discuss next. So, now, before I do that, I want to discuss what it is that I actually use when I work graphically. So when I work graphically, and I'm going to introduce a piece of software that I use to make my life a little bit easier, and you're welcome to do it. Now, of course, you're going to be required to use your calculators for much of the work that you do, and certainly when you take the AP exam, you're going to have to use your calculators. You're not going to have software at your disposal. So it's up to you. If you want to work with your calculator, that's fine. If when you're doing it, you happen to have a computer in front of you, if you just would much rather work on computer, as long as you know how to work on your calculator, that's fine. I just happen to, prefer working with online stuff. Occasionally I'll graph things by hand. Oftentimes I'll graph things on the computer. So before I continue with this problem, let me introduce this piece of software. When working graphically, I use the online grapher called Desmos. Many of you have probably heard of it. If not, not a problem. Grapher called Desmos, which is just at desmos.com. It's absolutely fantastic and so easy to use. Literally, it'll take you like 3 seconds to learn how to use it. So, when you pull up desmos.com, on the home page, you'll see a large red button. A large red button that says Launch Calculator. So you'll see this big button and it'll say Launch Calculator. Press that button. So press this button, okay, and you'll get a graphing screen. You'll get a graphing screen. At this point, you can just start graphing. Enter a function, start graphing. Now, start graphing. So, don't worry, I'm actually going to devote one of the next few lessons to a quick tutorial on what Desmos is. I'll go ahead and I'll pull it up, show you how to use it, show you how to enter the functions, and show you the few things that you're going to need. It's going to be very, very quick. If you want, just go to it and you can figure it out yourself. The little help button actually is very, very short. One thing I love about Desmos, it's very intuitive and there's not a lot of discussion in terms of the help. They present only what you need in very, very quick, easy, manageable terms, so you can start using it right away. So in any case, that's that. Now let's go ahead and return to the problem at hand. So again, we are concerned with trying to find an instantaneous slope, an instantaneous rate of change, the derivative, at a value of t equals 20. Well, let's see, where is it? Here we go. Okay, so essentially what I've done with Desmos is I've gone ahead and plotted the values. So at time, this is the time t, and this is the volume. At time 0, there's nothing in it. At 5, there's 30. At 10, there's 100 gallons. 15, 220. I've plotted these as points that you can see. Okay? Now, what I've done is I'm going to go ahead and connect these with individual line segments. All right? When I do that, I get that. So I have at least some sort of a rough idea of what this looks like. Now, again, mind you, this is usually a smooth curve, which we can use some numerical analytic techniques to find, but for our purposes, this is absolutely fine. Now, 20, so this is the point that we're interested in, right there. Now, let's go ahead and talk about what it is that we're going to be doing here. So the instantaneous slope that we're looking for means the slope of the tangent line through that point. Okay? So when you have a graph, you can actually find the derivative, the slope of the tangent line. Here's how you do it, by doing it graphically. What you do is you draw the best line that you can, the best tangent line to the curve. That's the best one that I could come up with. Okay, so that's the first thing that you do. So let's actually write that down. So draw the best tangent line. Draw the best tangent line. Okay. Next, what you're going to do is you're going to pick 2 points on that line. Pick 2 points on the tangent line. 3, you're going to calculate the slope between those 2 points. Use the 2 points to calculate the slope. So again, this is a graphical technique for actually finding the slope of the tangent line, the derivative at a particular point. If you don't have an explicit function that you can find the derivative of, you can just go ahead and draw out the best function, draw your tangent line, and then just pick 2 points. So I'm going to pick a point there and a point there, and I'm going to find out what they are. So in this particular case, let me see. Yeah, maybe 24, I don't know. The points that I ended up actually picking were the points, I think 24, it ended up being 500, so 24, 500, I read them right off the graph, and over here I think I ended up picking 15 and 175, so at the point 15, I go to 175, so that's that point. Drew my best tangent, pick those 2 points, and now I find my instantaneous slope. So my instantaneous slope equals 500 minus 175, change in y over change in x, over 24 minus 15, and I get an answer of 36.1. Okay, now, there is another approach that I can use. Let me go ahead and just describe it. I noticed that I have data points for 15, that's 15 to 20, and I have a data point for 25. That's 25 and 600. If I draw a secant line, I notice that the secant line in this particular case, it looks reasonably symmetric from this point to this point. So the slope of the secant line looks almost parallel to the slope of the tangent line, right? So what I can do if I wanted, I can find the slope of the secant line between this point and this point. That's another way of doing it. It's going to be the same. The only difference between this line and this line as far as slopes are concerned is you just moved it down. So slope-wise, parallel lines have the same slope. So if I want, for a particular point, a tangent line at that point, I can pick points that flank it, that I have values for, if it's reasonably parallel. In general, I don't do that. In general, I just draw the best tangent line that I can, and I pick 2 points on that line randomly, and I find the slope. So in this particular case, we found 36.1. Okay, now as far as the physical interpretation is concerned, so physical interpretation. Well, a slope is a rate of change. An instantaneous slope is an instantaneous rate of change. It is 36.1 gallons per 1 minute. In other words, 36.1 gallons per minute. This means that at time equals 20, so this means at exactly 20 minutes after I started filling up the tank is being filled 36.1 gallons for every minute that passes. That's it. That's all. Okay. Let's see. Okay, so again, I mentioned once before, let me go ahead and do this in purple. No, it's fine. Let's go ahead and do it in red. The particular thing that I've done with Desmos is I've connected these particular data points with lines. We know in general that it's not a line. There's going to be some sort of a smooth sort of function like that. Now, again, let me return to what it is that I mentioned early on. You're going to be a given function. In this particular case, volume is a function of time. You're going to be given a function in 3 different ways. You could be given a table, which you can graph. You could be given the graph, okay, just given the graph as it is. That's another way that you're going to be given a particular function. Or the third way is actually given an explicit function. For example, this could have been v equals, 1/2, t cubed, something like that. That's an explicit function of volume as a function of time that passes. So you could be given a table, a graph, or an explicit function. Now, here we use the table to make a graph, and from the graph we physically drew a tangent line, and from that tangent line we extracted the data. Now, the idea behind calculus is our preference is always to be able to find an explicit formula, because once we have an explicit formula, we're going to develop techniques, in other words, differentiating this and coming up with a derivative for this, so that some function of t, some v prime of t, which is the derivative of this function, so that at any place along t, I can just plug in a particular value and find what the instantaneous slope is. We're not always going to be that lucky. More often than not, we'll be working with functions because, again, we're teaching calculus. We're trying to develop the techniques of calculus. But understand that in the real world, oftentimes you'll be given a table of data that you'll have to convert to a graph. And you'll either work from the graph directly or use numerical techniques to approximate, find a function, and then from there work your, calculus magic.